Okay, in this video, we're going to continue working with imaginary numbers. The difference with these problems is that they will be presented in their raw negative square root form, and you're going to be expected to convert them into I form first before performing any of the algebraic operations that are suggested. Like here, you'd be doing a difference. Here, you're going to be squaring a binomial. Here, you're going to be reducing a quotient. Here you're going to be multiplying and adding various operations, all of them requiring you to convert to I form first because of these negatives underneath the square roots. That's what suggests that you have the I. So let's start by looking at square root of negative 49, which is really negative 1 times 49. I'm only writing it like this so that you'll see that the factors that make up negative 49, you actually can take a square root of that, which would be 7. And we've been presented in this section with a definition for square root of a negative underneath a radical, because all of this represents what's happening underneath the radical. This represents I. So I've converted that square root of negative 49 into 7I. That's followed by a minus sign. And then I can do the same thing here. Even if you don't write it as negative 1 times 9, you can still look at this and take the square root of 9, which is 3. Taking the square root of a negative underneath a radical square root symbol is I. And once you convert both of these negative square roots into their I form, it presents as a much simpler problem, where all you have to do to finish the problem is combine like terms. So this would be 4I. Is the final answer. In problem number 2, you're going to be squaring a binomial, but not until you convert to I form. So square root of 25 is 5I because of the negative in front of it. And I do want to keep stressing that these negative square roots, they're negative while they're underneath the square root, but when they come out in their I form, then they're positive. If there does happen to be a minus anywhere, it'll be because the problem has a minus in it, as this one did. But this came out as a positive 3I. This came out as a positive 5I. Bring that plus sign down, bring the negative 3 down, and you're going to be squaring. There's actually a shortcut for this. The long way to do it, which is probably how most of you are still doing it, is for you to realize what it means to square a binomial. It means that that binomial is going to be multiplied by itself. And to get that done, you're going to have to FOIL. So you're going to have to multiply for first times first, outer times outer, inner times inner, last times last. I will mention that you see that I'm going to be doing 4 different products, and a lot of students, a very common mistake is that they think squaring a binomial means just square the front, square the back, when in fact there are several more steps beyond that, as you see here. So following each of these arrows, we're going to be multiplying. Negative 3 times negative 3, that's going to be 9. Negative 3 times 5I will be negative 15I. And then coming down here to these bottom arrows, another negative 15I. And then this last arrow gives you 25I squared. And then continuing with that, we can clean this up. Putting this negative 15I together with this gives you negative 30I. And then this has a definition, just like square root of negative 1 is defined as I, the imaginary number I squared is defined as the real number, not imaginary, the real number, negative 1. So down here, you're really seeing 25 times I squared, but I squared is negative 1, so that last number is negative 25. And if you continue by combining the real number in the front with the real number in the back, you have 9 minus 25, which is negative 16, and then that negative 30I being the term in the middle. Excuse me. The shortcut for this problem is square double square. Just want to keep reminding you of these shortcuts. So if you are using this shortcut, you're going to square the front term, which is 9. Keep in mind that whenever you square something, it comes out positive. So this is going to be positive, and so is this. Whereas the middle term, you're going to have to wait and see what sign you get for the product, because that is actually what you're going to double. But if you square the front term, you get 9. If you square the back term, you're squaring the 5 as well as the I. So that would be 25I squared. And when you do the doubling portion, you multiply, which would get you negative 15I, and then you multiply it by 2. And that's what gives you the negative 30I that you saw happening here. Remember, the front square is positive, back square is positive. And you see that you have the same terms, a 9, a negative 35, and this would be the negative 25. I mean, it would be positive 25, but by the time you multiply it by what I squared is equal to, you write into this, and then that turns into that. So you get the same answer, but with less steps. So I just wanted to point out that shortcut to you as well. You can use that whenever you're squaring a binomial. In problem number 3, what happens that is new in this problem as opposed to problems 1 and 2 is that you have an imperfect square. This is not a perfect square, whereas these were. Square root of 49 is called a perfect square because there's a number that when multiplied by itself gives you 49, and that number is 7, which is why it was the square root, and of course the I coming from the negative. This is a perfect square also, because 3 times 3 is 9, which is what makes it the square root, and again, the I coming from the negative. In problem number 2, we had square root of 25, which is also a perfect square. 5 times 5 is 25. And then you come to number 3, and that's not a perfect square. So you're only going to partially be able to remove the root. What I suggest that you do in this case, although you can break it down into primes, is to think about things that you know the square roots of. Not starting with 1, because 1's not going to help you break this down any further. But the very next number after the square root of 1 that we have is 4 has a square root, 9 has a square root, 16 has a square root, 25 has a square root, and of course they go on and on and on. A good way of remembering how to generate this list is that these numbers simply come from 2 squared, 3 squared, 4 squared, 5 squared. That's where these numbers come from. These are the numbers you should use to break down that 45, because then you'll at least be able to take square root of part of the number. So the number from this list that divides into 45 is 9. It would be 9 times 5. Bring that negative down. And now I can take the square root of this part, the square root of 9. I'll write the beginning part first, so it's negative 15 plus. And when it comes to this part, you're taking the square root of 9, just like we did in the problems above, and also recognizing that the square root of the negative is I. So this will be 3I coming out of the radical as a 3I. So I've taken care of that and that. But the 5 has to stay underneath. So that's called taking a partial square root. I was able to take the square root of this part, the negative 9, but not of the 5. As far as reducing this quotient, if you see that all of these coefficients, all the numbers on the outside of the radicals, on the outside of the radical are considered coefficients, and if they're all divisible by some common number, then you can reduce it. And that number is 3. 3 divides into the front, divides into this 3i coefficient, and it also divides into the 30. I'm going to put that answer over here. Ran out of room. Okay, so negative 15 divided by 3 is negative 5. 3i divided by 3 is 1i, with that square root of 5 as the multiplier, and then 10 on the bottom. And that is your third answer. Answer for number 3, as simplified as it can be. Then in numbers 4 and 5, we have two perfect squares here, and then I'll give you another problem here where they have imperfect squares. So continuing with breaking down these square roots, again, let's put it in its I form first, then carry on with what's suggested here. These numbers out front are multipliers, so it's going to be 6 times whatever you remove, and I'm removing 9i. That gives me 54i. Bring down the plus sign. 4 as a multiplier, multiplied by whatever you remove, and I'm removing 6i. So that's positive 24i. This was going to be 78 with an I. And that's as simplified as that gets. And then the last problem, again, we're back to the imperfect squares. So you'll only be able to remove part of each one. And you want to maybe use these numbers from the square root list. The number that goes into 20 is 4 from the square root list. 4 times 5, don't forget that negative. I can remove this part as 2i. Okay, again, it's negative while it's underneath the square root. When it comes out, it's a positive I term. So I took care of those. The 5 remains underneath. Bring the minus sign down. Then from the square root list, 16. You want to pick the biggest one possible that goes into this. Otherwise, you have to break it down twice. So I know 4 goes in there, but 16 is even bigger. And it also goes into 80. So this is 16 times 5 with that negative there. You can remove this part as square root of 16 comes out as 4. Square root of that comes out as I with a 5 hanging off the back. So we removed these as 4i. 5, there's no square root, so it remains inside. And then when subtracting radicals, the radicants have to match, and they do. And when you actually subtract or add radicals with matching radicants, all you really do is combine the coefficients that are out front. So 2i minus 4i, that's how you actually combine common radicals. And then you hang that common radical off the back as a multiplier. So 2i take away 4i, negative 2i with a square root hanging off the back. And that is the final answer for problem number 5. So we've done 3 examples where there were perfect squares. We did 2 examples where there were imperfect squares and various kinds of algebraic operations, all with the underlying theme that you need to take any kind of negative square root, convert it to I form first, then perform the algebraic operations.